Hello everybody, we have been discussing flip-flops. So we have seen its truth table, characteristic equation, excitation table and also representation through timing diagram in an analysis problem. So in today's class we shall discuss conversion of flip-flops and flip-flop timing parameters. In course of that we shall also acquaint ourselves with synthesis of sequential logic circuit. We shall gently introduce ourselves to that more complex sequential circuit design we shall do later. Okay. So, here when we are talking about conversion of flip-flop, so what actually we are looking at is a situation where a circuit has been designed with a particular kind of flip-flop. Okay. And in your resource, in your stock or library, you find that a different kind of flip-flop is available with you. Okay. So, one option is to redesign the entire thing using the flip-flop that is available with you, or thinking of a conversion mechanism by which the given flip-flop, the available flip-flop can be made to work like a different flip-flop. Okay. So, if we are looking at D flip-flop is available with you, okay, and you are looking for a T flip-flop made out of 8. Okay. So, one such circuit we have seen in the analysis class in the previous class, but let us look at a formalized method. So, one way of doing it is that we know the characteristic equation of D flip-flop is Q n plus 1 is equal to D. So, whatever is presented at D input with the clock trigger, it goes to the output, that we already are familiar. Okay. So, if we are talking about conversion of D flip-flop to T flip-flop, so we know the T flip-flop equation, characteristic equation to be Q n plus 1 is equal to T Q n prime or that is plus T prime Q n. Okay. This is already we know. So, if you look at this equation, Q n plus 1 is equal to this and Q n plus 1 is equal to D, right. Then if this input T Q n prime plus T prime Q n we feed as D, okay, then the D flip-flop next clock instant it will go here at Q, at the output of Q n plus 1, right. So, this Q n plus 1 will take the value of D if D is defined as this one. Is it clear? Okay. So, simply we can write D as T Q n prime plus T prime Q n. Okay. And that in the logic circuit, this is the combinatorial logic circuit, right. So, we can get by designing it. So, this is your T input and this is just an XORing. So, basically Q and Q n getting XORed and it is being available here as D input, and when the clock trigger comes, whatever is here it will go there. Okay. So, whatever is here, that is this will go there. So, this is very simple for converting D flip-flop to T flip-flop. Okay. So, this can be extended to JK flip-flop as well. So, JK flip-flop equation is similar, but it is J Q n prime plus K prime Q n. Okay. So, we will take D as this one, okay, and then we shall just make a combinatorial circuit and accordingly we will get it, right. And similarly for D flip-flop getting converted to SR flip-flop. Okay. So, the equation is Q n plus 1 is S plus R prime Q n. So, we can write S as D as S plus is here, or we know that. So, R prime Q n. Okay. So, the circuit will be here, S goes here, it is getting ORed with R, there is an inverter, a NOT gate, okay, and Q n is coming from here, right, and this is ANDed and together it goes here, right. So, this block entire thing can replace the SR flip-flop wherever it is required in your design, okay, in your circuit. Okay, is clear? Now, if we are looking at converting other flip-flop to D flip-flop, right. So, if we are looking at SR flip-flop getting converted to D, we have seen before, otherwise also we can figure it out from their equations, okay, the characteristic equation. This is Qn plus 1, okay, is equal to S plus R prime Qn, and if we consider S as D and R as D prime, which we had done before, but we can put it in the characteristic equation, and in this equation S is put as D and R as D prime, okay. Then we go through the steps, we can see that Qn plus 1 is becoming D, if that is what is done, okay. So, this Qn plus 1 is D is basically your this D flip flop equation. So, SR flip flop, right, S and R, this is your clock, right. So, here you put a inverter and you connect. So, this is D. So, this whole block, this is Q, this is Q bar, this whole block will behave like a D flip flop, okay. Now, same thing if you follow for JK flip flop, again you put a D and J as D and K as D bar, right. So, you can see J as D and K as D bar, and then you go through the simplification steps. So, you see that it is ultimately becoming D ANDed with Qn prime or Qn, which is D only. So, you can get the D flip flop just by connecting an inverter between J and K and taking the J output as D output. So, the entire block over here, okay, behaves like a D flip flop. Okay. Now, if we are looking at converting T flip flop to a D flip flop, okay. So, now if you look at the equation, whether we can put an inverter and all and we can get it, we can see that the solution is not as trivial as it had been the case before. So, if we look very closely and go through algebraic manipulation, we can arrive at something, okay, but we can look at a method which is a generalized method which will work for every such conversion or every such synthesis kind of thing, which will work equally well for what we have shown here. Okay. Here we got by comparing the equation and by applying some knowledge about this Boolean algebra. Okay. So, otherwise also we can follow a standard synthesis method by which we can arrive at this solution. So, let us look at this problem of getting a D flip flop out of T through a synthesis example, synthesis of logic circuit example, okay, not going through a algebraic manipulation process. Okay. So, to do that, so let us see how we can go ahead. So, here what we are doing, you see we have a table here, right, which has got 4 columns, and here we have got of course, this 5 rows where data is 4 rows where data is put. Okay. And so, the first part of it, you see the one in this color, right, yellowish color, you see that it is D flip flop truth table. Okay. The flip flop that we want, okay, truth table of that would be written. So, that is this generalized method we are talking about. So, it will apply for any other case. We shall look at another example, of course, in the next slide. So, here we are talking about D flip flop. So, D flip flop truth table is here. So, 0, right, if Qn is 0, the output will be 0, Qn is 1, output will be 0. That is the way D flip flop works. So, if D is 1, both for Qn is equal to 0 and 1, output will be 1. This is okay, right. Now, we look at the T flip flop, right. So, this is the D flip flop, that is the way it would work. So, at that time, at the T flip flop input, because inside there is a T flip flop, as a whole the block T flip-flop plus some additional circuitry, it behaves like a D flip-flop. So, inside whatever T flip-flop we have put, what should be the input in these cases, 4 cases that we have seen in the D flip-flop truth table. Okay. So, that we figure out. So, we see that in the first case when D is equal to 0 and Qn is equal to 0, okay, then the transition takes place from 0 to 0. Okay, Qn plus 1 becomes 0 for this combination, right. So, for this particular transition 0 to 0, right, what should be the input at T flip-flop? So, we look at T flip-flop excitation table. So, that says it should be 0. When this is 0 1, this combination, and next value is 0, it toggles. Okay. So, for T flip-flop the input should be 1. For this combination 1 and 0, next value is 1. So, that is again 0 to 1 T flip-flop toggles, that is input should be 1, and the fourth combination when 1 and 1, then the transition takes place here is 1. So, 1 to 1 T flip-flop should be 0. Is it fine? So, this side we are getting from excitation table, put in this color, and this side we are getting from truth table, right. So, we have put them in one common table. Okay. So, now we understand that for this combination D and Qn, okay, that is external input and current state, what should be the T flip-flop current input? Okay. So, to get equation out of this, what we can put? We can get it through a Carnot map, I mean simply. So, D is over here, that is 0 and 1, and Qn is 0 and 1. Now, we look at the cases. So, 0 0, T is 0, 0 1, okay. T is 1, this is the 1, 1 0, this is 1, so this is 1, and 1 1, this is 0, right. Now, what we find that this can be obtained only by through two such product terms. So, D Qn prime plus D bar Qn, okay. This is what it becomes. So, T becomes actually D XOR Qn, right. So, you could have obtained it by, as I said, through algebraic manipulation and all, and knowing how XOR function works, XOR of same function with the same XOR of one function with the same function is giving you 0, right, and 0 with another variable will be the variable itself, okay. 1 XORed with the variable is complement of the variable, and 0 XORed with the variable is the variable itself. So, essentially what we are getting here is XOR of XOR and then the variable, okay. So, that if we are knowledgeable about the XOR operations and all, otherwise as I said, generally speaking, we can get it for sure by a standard method like this, okay. And we can verify. So, Qn plus 1 over here we have got in this manner. We know the basic equation of Qn plus 1, sorry, that is T Qn prime plus T prime Qn for this particular flip-flop, right. And then we substitute T as what we have got, Qn and D XORed, right. So, that is this relationship, and over here, okay. Then we do go through the steps, right. Then we can see that it is nothing but D, okay. So, Qn plus 1 eventually becomes D, right. So, this is the way we can see that it is the T flip-flop and this is the D flip-flop. So, this is a simple synthesis problem. These steps we know that truth table, and then this is the what is required for the input to be in all those cases, and that is obtained through excitation table, okay. Now, let us look at another example, okay, where we have JK flip-flop required from SR flip-flop, okay. So, given a SR flip flop to to input, and we require a JK flip flop. We can do it for any other type, as I said, one type to another. So, let us look at this one, right. So, in this case, what we have over here in the first place, as we have mentioned, so JK flip flop truth table. Is it okay? So, the one that we want to be made, that truth table will be put, okay, that is there in the left hand side, right. So, 0 0, and if this is the case, input is 0 0 0 0 0 and Qn is 0, right. Then next value will be 0 only, and input is 0 0 and this is 1, next value is 1, because 0 0 the previous value is written, okay. So, 0 1, okay, irrespective of what is Qn, this is 0 0, 1 0, irrespective of Qn, this is 1 1, and when it is 1 1, it toggles, okay. So, 0 becomes 1, 1 becomes 0. So, this we are already familiar. Now, in each of these cases, now for the SR flip flop that is being used for the design, at its input, what should be present, okay, that we figure it out, okay. So, here we see a 0 to 0 transition, okay. If Jn is 0, Kn is 0, Qn is 0, at that time, okay, what should be present at S and R? Since it is a 0 to 0 transition from SR flip flop excitation table, we can write it should be 0 cross, that means either 0 0 or 0 1, any one of them is okay, okay. So, this is what should be present, clear. So, if it is 0 0, instead of 0, if it was 1, okay, then what would have been the case, the transition, it would have moved to 1. So, what should have been present at SR flip flop input at that time? It should have been X and 0, okay, that is from the SR flip flop excitation table, right. So, for this combination 0 1 0 JK Qn, then at that time 0 to 0 transition, again 0 X, 0 cross, okay, 1 to 0, we need 1 to 0 is 0 1, right, 0 1. So, again 0 to 1, okay, so this is 1 0, 1 to 1 cross 0, 0 to 1 1 0 and 1 to 0 0 1. Is it fine? So, this for this particular transition we require this, okay. So, we can now understand that this part is the SR flip flop excitation table, which is deciding the entries, right, and this part JK flip flop truth table are deciding the entries. So, this is this JK flip flop truth table itself. Is it okay? Now, with this table in hand, okay, we now move to next step. So, next step would be that representing each of these input, okay, Sn and Rn at a given time in as a function of Jn, Kn and Qn, okay. So, the current state, current inputs that is coming from externally, because we are trying to convert it to a JK flip flop, okay. So, that is what we are having as current input, and at that time what should be presented at SR flip flop input, so that required change in the output Qn, required Qn plus 1 value appears at the output. Is it fine? So, from that truth table, the truth table that we had just seen, do a mapping, okay, from this part Jn, Kn, Qn, okay, and Sn, and then Jn, Kn, Qn as Rn. So, two such Karnaugh map will be there, two such relationship will be available, okay. So, in one case this is what we get, right, 0 0 1 1 cross 0 0 x, right. This you can see from so 0 0 0, you can see for Jn, Kn, Qn it is 0 Sn. So, you can see it is Sn, right. Here 0 0 Qn is 1, this is x, okay. So, you can see this is x, 0 0 1, this is x. Next is 0 and 0, right, you can see 0 0. Next is 1 1, you can see. Okay. So, this is the OA 1x, right, and then 1 0. So, 1x and this is 1 0, because this is 1 0 and this is 1 1, that is the OA Carnot map is written, right. So, 0x 0 0 1x 1 0. So, this is what you can see, this is what you can see over here, 0x 0 0 1x 1 0. Okay. So, similarly for the Rn value, you can see the mapping is presented. Okay. x0 x1 0 1 0 0. Okay. So, now to have a minimized expression for this, right. So, we can see that one group is required here. So, that is coming as Jn remaining constant with value 1 and Qn with value 0. So, Jn Qn bar. So, Sn we can simply write it this way, because we need to cover only the ones. Okay. That is the largest group possible, and for Rn we can see that it is Kn remaining value with 1 and Qn with value 1. So, it is Kn Qn. Okay. So, now we can get the circuit as we see over here. So, this is your basic SR flip flop, this is your Q and Q bar, right, which is generated internally in the SR flip flop. So, J and K are the external input. Okay. So, in one case J is ANDed with Qn bar, right, the connection is taken and fed as S, and in the other case K is ANDed with Qn and fed as R. Okay. And this whole block which you see in the dotted box is your this final circuit, okay, final converted circuit. Fine. So, any flip flop that you require, which is from the characteristic equation or truth table, you can directly cannot convert. Okay. You can go through the synthesis process. First you write the truth table, and then for the changes that is happening at Qn and Qn plus 1 for a specific input, you write the input that is required for the flip flop being used from the store, okay, or library, and then you use the excitation table through Carnot map or any other minimization process. You get the combinatorial circuit made, and then finally you implement it. Okay. Right. Fine. To end this particular lecture, we just would like to get introduced to another important concept, is that of flip flop timing parameters, its significance. Okay. So, as I said, the timing diagram is the key to exhibit how the things happen, work out with respect to time, which is not very clear from the truth table, excitation table, or other form of representation. So, we take help of this timing diagram to discuss, to understand the importance of these timing parameters. So, there are quite a few, but we just take up three important ones. So, one is called setup time. Okay. So, this is minimum amount of time data must be present before the clock trigger arrives. Okay. So, the clock trigger comes. So, if it is a say positive edge triggered kind of thing, it has arrived. Okay. So, whenever it reaches positive, it is is susceptible to change. So, before that some minimum amount of time data must be held at a stable value. So, this is called setup time. Okay. If it does not, then the output cannot be guaranteed, manufacturer cannot guarantee the output. Okay. So, this is one aspect, and the other thing which comes in association with it is called the hold time. Okay. So, this is the minimum amount of time data must be held after clock trigger. Okay. So, clock trigger has happened, you are not supposed to immediately withdraw the data. So, it must be held for some time. Okay. The minimum time that is required, if you hold it for more time, there is no issue, but certain minimum time it should be held, that is called hold time. Okay. So, that is to ensure or guarantee appropriate output of the flip flop. appropriate state change in the flip-flop. Okay. And the other thing that is there is called propagation delay, right. So, time taken for the output to change after clock trigger in response to the input. So, basically it goes to different logic gates, and there could be various passive components like stray capacitances, resistances, so charging, discharging. So, all those issues are there because the basic gates we have already learned. So, if you put together all of them, okay, so the amount of time that is required for the for example here d was 1. So, d is after clock trigger becoming, initially it was 0 becoming 1. So, the delay associated is called propagation delay. Okay. These three terms you take note of, and if you go through the data sheet, you will see many other such terms are there, timing related, which are important. Okay. But that may occur in certain instances of time, not regularly as it is happening for the setup time, hold time and propagation delay. For example, if you present a asynchronous clear, right, or asynchronous preset. So, after certain amount of time only it will be reflected, the output will get cleared or it will get preset. So, there is a delay associated with it, but it is happening whenever it is required, not regularly. So, those delays and those parameters, those terms are also available in the data sheet. If you look at it, you can see that they are there. Okay. So, to get an idea about what are the practical values, some of the ICs or circuits that are used. So, we take the D flip-flop, one from TTL family, okay, another from CMOS family. So, you see that in TTL family the setup time is, these are all in nanosecond. Okay. So, minimum time 20 nanosecond, hold time is 55 nanoseconds. So, 7474, 74LS, 74A. Okay. So, if it is again L means low power, so higher resistance values. Okay. So, if it is only Schottky, S for Schottky, that we know, we have seen it in the logic family. So, then the resistance values will be standard 1. So, for which you will see the time will be relatively less. So, these are just the order that you get it, but for different families with different realization, you will be having variation around it. Okay. And this propagation delay, so low to high 25 nanosecond. Okay. And this is 40 nanosecond is high to low. Okay. This is the maximum delay, okay, that can happen. And typical frequency of operation because of these delays and all, so that is 33 megahertz. Okay. And in this case, this CMOS thing, so you can see the setup time is like this, hold time is approximately 0. In some literature, you will find that it is written 0.5 nanosecond. So, this is the propagation delay. It has not been separated in the data sheet low to high, high to low, and F max has been mentioned as 50 megahertz. Okay. So, to summarize, conversion of D flip-flop to any other flip-flop is straightforward if we consider the characteristic equation. Conversion of SR and JK flip-flop to D flip-flop can be done by comparison of their characteristics. The conversion of T flip-flop to D flip-flop can be posed as a synthesis problem. In this, D flip-flop truth table and T flip-flop excitation table are required. And similarly, SR flip-flop can be converted to JK flip-flop again through a synthesis problem. Okay. And setup time, hold time, propagation delay are important timing parameters for their reliable operation. We need to take note of them and use the flip-flop triggering accordingly. Thank you.